This motion picture is the result of research done on behalf of ADCI by Dr. Lester Garber. The work was sponsored by Prince Corporation and performed at their facilities in Holland, Michigan. Wave celerity during the slow shot phase is studied using the water analogy technique with a transparent 3-inch diameter cold chamber. The ratio of viscosity and density of liquid aluminum at casting temperature is similar to that of water. Therefore, the wave formation reacts the same for the water used here as it would for aluminum. This will show an example of a velocity that is too fast. The cold chamber is 50% full, which is above the minimum of 40% that is recommended and within the normal range. The actual speed in this sequence is 23.6 inches per second as compared to the critical cycle speed of 19.6 inches per second. As this wave progresses, the crest can be observed, which breaks over and forms an air pocket as the wave degenerates in turbulent action. Theoretical formulae have been developed to determine the optimum slow shot velocities under many different conditions. This has been called the critical slow shot velocity, and a table is available that specifies it over a wide range of cold chamber diameters and fill levels. The dark material that is visible at the bottom of the chamber is ground-up plastic, which has a specific gravity slightly higher than water. The purpose is to show the degree of turbulence. Here again, the cold chamber is 50% full at the start of the cycle, and the velocity is 15.2 inches per second. Compared to the critical velocity of 19.6, this is as slow as the first scene was fast. The wave does not quite reach the top of the cold chamber, and the air bubble starts to form on the back side of the wave. As the plunger continues to move forward and the chamber fills with liquid that encapsulates the air, it has no chance to escape. As we saw in the first sequence, a velocity that is faster than critical generated a wave that breaks too soon. It forms turbulence and an air pocket in the front of the wave. Then, this second sequence shows that a velocity that was slower than critical results in a wave that never reaches the top of the chamber, and an air pocket is formed even though there is less turbulence. In either case, this entrapped air is then carried directly into the die cavity through the runner system and cannot escape through the vents because it is surrounded by liquid in this case. In actual die casting, it is liquid aluminum. It eventually forms porosity that many times is objectionable. Now, this next scene, which also considers a 50% fill condition, is closer to the critical speed at 19.2 inches per second. A slight roller is formed, but with much less air entrapment near the end of the phase as the liquid fills the system. Only a few small bubbles can be seen along the top that were probably a function of a problem in the test stand plunger. This phenomenon also occurs in all but the first sequence and has no bearing on the overall validity of the research. Dr. Garber was assisted in these experiments by Alan Vandenberg while he was at Prince, who also operated the high-speed motion picture camera. By this reference, we acknowledge the excellent quality of the photography. To emphasize the relationship of the critical slow shot velocity to the variables of cold chamber diameter and the fill level percentage of the cold chamber, a view of the chart is shown here. As you can see, the symbols at the top are similar to the scenes that you have just viewed. The chart covers cold chamber sizes for inside diameters of 1 inch to 6 inches in 1/4 inch intervals. The initial fill percentages are shown in the extreme left-hand column, and the critical or ideal slow shot velocity is located to the right and directly under the appropriate cold chamber diameter. The last scene, you will recall, had an initial fill level of 50%, and the same 3-inch diameter cold chamber was used. The chart suggests a slow shot velocity of 19.6 inches per second. The actual velocity was 19.2 inches per second, which is very close. it is obvious that most of the entrapped air has been eliminated. This is an example of the result that can be anticipated when the chart is used. If you do not yet have a copy, any die-caster can obtain one from the ADCI National Office. The purpose of this scene is to show the front of the chamber adjacent to the runner in more detail. Later on, the liquid will be seen entering the runner in the form of a slight pink vertical line moving upward on the right-hand side of the screen. The fill here is fairly smooth, even with a velocity of 16.6 inches per second. In the introduction, it was mentioned that wave celerity is being studied in this research. The definition of wave celerity is the velocity of a wave in relation to the velocity of the rest of the liquid. As an example, in this sequence, the velocity of the liquid is 16.6 inches per second, and you can see that the wave is moving at a different speed. Also, notice that the liquid is traveling up the runner before the cold chamber is full. For those of us who had always had a mental picture of a nice solid mass of liquid aluminum in front of the gate orifice, this may come as quite a shock. The change in liquid levels seen here is not significant, as it is caused by refraction from the outside shape of the shot cylinder. The last scene depicts a cold chamber that is 75% full at the start. This high level emphasizes the logic that there is less chance for air entrapment at higher fill levels. As a matter of fact, anything less than 40% produces such poor results that no lower levels are charted. The velocity here is 10.4 inches per second, which is very close to the critical speed of the 9.9 inches per second. The fill level is smooth, illustrating almost an ideal condition for minimum air entrapment. The data in the chart of critical slow shot velocities has not yet been confirmed by actual die casting of aluminum. However, many members of ADCI have reported good success when following the chart. This research is all based on a constant velocity principle at zero acceleration during the slow shot stage, which is representative of most of the die casting machines in the field today. However, there are some machines available with a constant acceleration from zero velocity up to the fast shot velocity. Dr. Garber is now working on the theoretical formulae that will also study this condition, and the high-speed camera will soon be used again in a similar fashion to that which you have just seen. We hope that this motion picture has been helpful to die casters, not only for an explanation of critical slow shot velocity, but also for the opportunity it provides to observe the flow patterns that occur in the cold chamber under different conditions.